Okay. So you should be seeing PowerPoint slide. Okay, if you don't see it, then you just let me know. Otherwise, I assume that you can see it. You see actually a kind of blackboard. It's a PowerPoint. Okay, it's blank. Not worry, you see blank. That's what you should be seeing. Okay, so we're looking today at the linear regression. Okay, linear regression. Regression analysis is actually obviously very important in the context of survey research. So, as you must have again gone through yesterday with Dr. Robin, so very often when you do research in social sciences, the goal of a research is to explain a certain phenomenon. We are interested in a specific phenomenon, a certain outcome, we can say. And therefore, we have a certain theory that we'll want to test. The theory in its simplest form can comprise, therefore, of only two variables. The outcome, the phenomenon of interest. That's the phenomenon that we want to explain. Okay, the phenomenon that we want to explain. And how do we refer to this one? We refer to it as the dependent variable, okay, when we're going to measure this phenomenon, this concept. So we refer to this as a dependent variable. And we have a number of other names which we can give to those, to it. So we can refer to it as an outcome or to maybe the explained variable. And there are other names, other terminologies that you can use. Most importantly, that's what we want to explain. Okay, that's what we want to explain, and we can go further and say that's what we want to predict. Okay, that's what we want to predict. And basically, our research, if you're doing such a research, just as an aside here, just to remind ourselves, we're dealing here with a deductive research using a deductive approach. Research also using a quantitative methodology. Okay, where we want to test. So we're using a deductive approach, we're using quantity methodology, but we want to test a theory. So this is where, okay, when it comes to analysis, linear regression comes in handy, very useful, because it allows us to test a whole theory. So you're doing a research, you come up with a certain theoretical framework, isn't it? You propose a framework, you propose a theoretical framework. Sometimes you can, now we can use different terms, conceptual model, conceptual framework. It does mean different things if we want to be really peculiar about it. Theoretical framework, conceptual model, whatever. Let's put, that's another a debate in itself. But the most important thing is you have an outcome, right? You have an outcome, and there's a logical reasoning behind which we can propose a model, a framework where we are going to. Sorry, I'm just unmuting students. This is why I'm just stopping again and again. So I just need to click on the unmute button. It'd be good if all students could join in. Let's say as soon as possible, so that we don't have to do that again and again. Right. What I was saying. Yeah. So at the end of the day, whether you refer to it as a conceptual model, conceptual framework, theoretical framework, okay, whatever, notwithstanding the small differences which we have between those, at the end of the day, we're using a deductive approach. So based on existing knowledge, based on existing theories, we come up with a certain framework model which we want to test. Very importantly, we have an outcome which we want to explain, and we explain it using a set of different other concepts, All right, it could be 1, could be 2, could be 3. In its simplest form, it could be only 1, isn't it? But it could be 2, it could be 3. Different concepts which allow us to explain, to predict that particular outcome. How do we refer to those concepts? We refer to those when we're going to measure it. We're going to refer to those as independent. That's our dependent, the outcome, and those are the independent variable. Instead of here explained, we can refer to that as the explanatory variable or variables, right? So those are the different predictors. If we use the word outcome, we're going to say that's a predictor. Okay, so let's just call it predictor 1, predictor 2 for the sake of explanation, right? Predictor 2, predictor 3. So very often we want to test a model like that. Again, in its simplest form, it could be only 1. It doesn't really necessarily have to be 2, 3, 4, 5. Right? But most of the time, if you are using really a pure deductive approach, you'll be proposing a model where you have multiple independent variables, multiple predictors. Good. Now, when you speak about regression, we do have different types of regression. Linear regression is one type of regression. We do have other types of regression. For example, we have logistic regression. And here, logistic, we can differentiate between binary logistic and multinomial logistic regression. We also have ordinal regression. We have log linear regression. And so on and so forth. Actually, there are so many types of regression. Okay, we have very specific regression techniques as well. For example, lasso regression. We have binomial regression, Poisson regression, depending on the type of distribution you're looking at. So we have so many. We're not going to look at the specific type of regression analysis. It could be that for a particular research you're doing, even for your dissertation, that you need, for example, to use logistic regression, and then you will need to do some additional reading. But let us say that the principle behind those are the same. Okay, the principle are the same. Building on the core principle of regression analysis, we do have, depending on the specific research you're doing, more advanced type of analysis. For example, you might have structural equation modeling. Or if you're using time series or panel data, you might be using specific techniques. For example, using a VAR, vector error autoregressive, and vector autoregressive model. Or a VCAM model. Okay. So you have so many techniques which are regression based at the end of the day, which you can use. Okay. We're not going to cover those. Okay. In this particular module, we cover linear regression, which is the most used one, we can say, and which is like let us call it the classical, if you want, regression type. Okay. And then if you have, in specific context, specific conditions, and you might use other specific techniques, which are regression-based techniques at the end of the day. Same principles apply. It's just that the purpose of the analysis is very specific, given certain conditions, and therefore you have specific techniques which are best suited. Okay, so that's just an aside. Okay, let's keep that in mind, and let's come back to our linear regression. But the linear regression, obviously, you wanted to know it very well, at least when it comes to the application of it. Okay, so if we are speaking about linear regression, what we need to be very clear on, c'est que the outcome needs to be measured on a numeric scale. You will recall in terms of measurement and scaling. So if we speak about different types of data, different types of variable, we have numeric data and non-numeric data, isn't it? Non-numeric also referred to as categorical. If we're doing linear regression, it's understood that we're dealing with an outcome which is numerical, okay, measured on a numeric scale. It cannot be categorical. If you, I mean, you can have a scenario where here you have an outcome which is dichotomous, yes or no, for example. And this happened quite often as well, even in survey research. It could be secondary data as well. It doesn't really matter what's your type of data in terms of whether it's primary or secondary, by the way. But if you have dichotomous variable, then you need to use logistic, and more specifically binary logistic in that case, if you have a yes or no question as your outcome variable. Okay, but we're not dealing with that here. We're dealing with a scenario where you have a numeric scale, and therefore we are going to make use of a linear regression. So most of the time, if you are collecting primary data, at least, you'll be making use of Likert scale questions. And when you make use of Likert scale questions, especially if you have multi-item scale, which is actually what you will be encouraged to use to measure any particular concept, then we proceed and calculate what we refer to as a composite score. So you just take the average. In that case, right, we can assume that we are using numeric scales at the end of the day. Okay, and that's why, in fact, you will see that in the majority of studies in social sciences, in management, in even psychology, etc., let's say management, business administration, we make use of linear regression, just because here we're using Likert scale questions most of the time, which can be considered to be numeric, and therefore that's a type of outcome that we're trying to predict. All right. So that's one important thing, the dependent variable, numeric scale. What about the predictors? The predictors could be numeric, and most of the time we're going to deal with numeric scale, Likert type scales, considered to be numeric most of the time. But we can also include what we refer to as dummy variables. Okay, and I'm going to explain that in more details afterwards. It's not difficult, but let's say just to make the introduction, otherwise I'm going to go into detail here. So just make a note here. It could be a numeric scale or dummy variable, which I'm going to explain what it is. Nothing difficult. Okay, now we're clear about it. That's when we are going to use regression. We have a model which we want to test, right? Which is the case most of the time if we are using a deductive approach, a quantitative methodology. Okay, very often we have this scenario where we want to test a certain model, and we will want to therefore use a linear regression technique to test this particular model. We still have students waiting to unmute everyone. Yeah, okay. Okay, we don't want the one in waiting room again. Okay, sorry. So you are still in the waiting room. Okay, so let's now look at how to perform a linear regression analysis, okay, how to do it, and how to interpret the results, most importantly, as importantly. And to do that, I think, so I'm just going to make use of a concrete example here, okay, based on an existing data set. And if we have time, we're going to look at two different examples, but let's look at the first one. Suppose we have a research question. So let's start from scratch. So we have a research question. Now, suppose we're interested in the topic of academic performance. This is something which is always interesting to look at, isn't it? That's our phenomenon of interest. Okay, academic performance. That's what we want to predict. This is what we want to explain So we want to, we have a certain theoretical framework, a theoretical model, and our outcome variable is academic performance. That's what we basically want to explain. Okay, we have certain predictors, and that's what we'll do. Okay, let's have a specific research question here. So let's say do study time study motivation and let's stick to this first, and then we're going to add something to it. Let's say do study time and study motivation of, well, to make it interesting, let us take a kind of scenario here. Suppose we're looking at academic performance of HSC students. Okay, HSC students in 2021. That's what we're looking at. Okay, so suppose the results have just come out. Okay, so we got the results, and CO2 given the COVID-19 situation, etc. We really want to understand. We let us say we see that there's a lot of variation in ACAD performance, and we want to try and explain that variation. So why is it that some students have worked very well, some have worked very poorly, and we want to understand that better. So we propose a model based on existing theories, on existing knowledge we have. So we have identified, let us say, two different predictors, two different independent variables, and those are study time and study motivation. Okay, I hope so far so good. So the full research question is, do study time and study motivation of HSC students, of course, in Mauritius. I would not say that, of HSC students. So influence their academic performance. Okay, so that's our research question here. So if we want to represent that, okay, in our nice diagram here, so we have academic performance as our outcome, isn't it? And we're saying we want to test for the effect of study time and study motivation, isn't it? Okay, study time, study motivation. Obviously, what's the next thing you want to do? We have a research question. If we're doing quantitative research, if we are using a deductive approach, what is the next step? So you have a research question. What is the next thing before we, of course, collect data and perform the analysis? Okay, and this is something we're going to say we did. We're going to proceed and do the analysis. But before that, what do you want to do? There's something you really want to specify here. Who can tell me? Anyone?
Theoretical background.
Yep, so that's true, Dhananjay. So you need to have a theoretical background. So that's a good answer. Not what I was expecting, but that's a good answer. So of course, that's going to be your theoretical framework, and you need, of course, to write a full literature review, okay, where you have your theoretical background. Okay, that's true. Okay, so of course, that's not something we're going to do here, but that's something you need to do, okay, to support this model. Yep. But what do we want to do in terms of really kind of specifying before we proceed with analysis? Something which is
finding the variables.
Yeah, please say again.
Find our variables.
Yep. So actually, so those are going to be the variables, right? So we have study time, study motivation, and ACAD performance. And I think what you mean here is, of course, you need to know how you're going to measure it. each concept, how you measure it, and therefore translate it into variables. Yep, that's right. What else?
Your hypothesis.
Yeah, exact. Oh, Rubin is here. Rubin, go ahead.
No, so I'm just checking whether most of my students are here, Varian. So you carry on. I've got another lecture.
Yeah, good. Yes.
Okay, so take care, guys. Have fun.
Okay. Yes. So exactly. So we need to have a hypothesis, right? So how many hypotheses do we need here? We are going to have two hypotheses, one for each variable. Good. What's going to be your H1? Therefore, H1 is study time as a positive effect on academic performance. When you can specify positive, or sometimes it's recommended not to you don't really need to specify. So as an effect, okay, a significant effect, you might say on academic performance, what's your H1, and what's going to be your H2? Study motivation as an effect on academic performance. And again, you can, if you want to specify, we're saying here among HSC students. Okay, and again here, among HSC students. That's good. So you have your hypothesis. It's spelled out. C'est sous-entendu, bien sûr, that you have your null hypothesis for each, okay, your corresponding null hypothesis. Anyone can tell me for your H1, what's going to be your null hypothesis?
Study time does not have an effect on academic performance.
Yep, exact. Arjun, yep, that's right. So the null hypothesis is always the hypothesis where you say there is nothing, there's no effect. So your H node here will be that study time has no effect. What to be H2? Obviously, study motivation has no effect. Okay, so your H node is, we assume status quo. There is nothing actually, so there's no effect. So that's something to keep in mind. When you're writing your report, when you're doing the write-up, you don't need to actually write the H node. You don't need to write it, but that's something important. But because when you interpret the results, you always interpret the results based on the H node. We always, when we're going to draw conclusions, once we do the carry out analysis, as you already know, it's always about whether we are rejecting the H node or failing to reject the H node, right? Because that's the assumption. And this is how we work out intervention statistics, at least when using what is known as a frequentist approach, isn't it? Yeah, okay, so we're good with that example. I hope so far so good as far as the example you're using here is concerned. So we have academic performance, which we want to explain, which we want to predict, and we are looking here at two different predictors, two different independent variables, which are study time and study motivation. Now let us proceed and let us do a regression analysis, and then we're going to look at it step by step. Okay. Don't worry, for those of you who are looking at this for the first time, some of the terminologies will be a little bit like intimidating in the sense that you're hearing it for the first time. The good thing is that we're not going to really dwell into the calculations part of it. We're not going to look at the formulas and calculations. We are looking strictly at the application of it. Okay, so we want really to make sense of it and to understand the logic behind what you should be able to do as a master's level student, when doing your research, is to be able to carry out the analysis and especially be able to interpret the results very clearly. I'm sure many of you, you've done research already at undergrad level, and you will have noticed that the process is the same, actually. There's no difference. I always like to tell students, I think I must have mentioned that already. You need just to think about it like you're playing a sport. Let's say some of you like to play football, some of you like to play badminton. If you play the sport, you might do it at different levels, isn't it? But football is football, badminton is badminton. You can look at the best player in the world, best badminton player, playing best football player, playing whatever he or she is doing. It's the same. What are you going to do? You're just about kicking a ball. You're just about intercepting a ball. In badminton, it's about doing a smash. It's the same thing. It's just you do it better. You do it better. The clarity, it's just that the movement becomes more and more perfect. You improve on that. So the same thing when it comes to research. The process is the same. There's no difference in terms of the process. It's just the level. It's just the clarity. It's the yeah. So it's about just doing it better. Okay. So if you've done a regression analysis in the past, now at master's level, you make sure that you understand it better, you understand the logic better. You do some further reading. We might not cover everything in the lecture. That's not the goal because we still have, you see, we have one module only. We need to cover the essential stuff with you. At least you have all the foundation right so that you can, after that, it is easier for you to navigate your way through this maze of research methods afterwards when you're doing research. The thing is that, yeah, you should aim at better clarity, high level of understanding, being able to apply better. So this is what we aim to do, right? We're aiming at. Good. So let's look at the application now. So what I'm going to do straight away is just take an existing data set here. All right, take an existing data set, and we're going to run the regression. Okay, so let me explain to you the data set. So you're all quite familiar with SPSS software already. Well, normally we do this lecture in the lab. So I mean, it's not the same. It hasn't been the same for you this time. But trust me on that. It has been difficult for us as well as lecturers to cope with it. Okay, to find ways to teach the same thing online. Yeah. So, but I mean, at least we have a way to do it. Okay. You can imagine if we had the COVID-19 pandemic some 20 years ago, it would have been a catastrophe. We would have stopped everything, and then yeah. Anyway, we'll be able to cope. So that's the data set. We have your list of variable here and variable view. Okay, the variable which are of interest to us, academic performance. That's the variable we are going to use here, and then we have motivation. That's your second variable. Let me just write it the same way as I wrote in the explanation. So study motivation, hours of study. That's study time measured in hours. Not problem. So those are our variables, and what's academic performance? Okay, so let me have it academic performance of HSC students. So to make it align with the scenario we have taken. Okay, so what's the variable? Those are the variables of interest to us, okay, which we're going to use. And you can see in data view, we have a data here, motivation, acad performance, hours of study. Now, maybe what we should note is how we have measured the variables, okay, before we can proceed with the regression. So let's be very clear about those. So this is 1 to 7, and this is hours study per week, okay. So in terms of how we have measured it, so let us maybe just clarify that, and then we can proceed. Oops. For some reason, the menu is not appearing here, so that I can write what just happened here. How do I hide what? I just want to hide anything. Okay. Sorry for that. Okay, so academic performance. What's our outcome variable? How's it been measured? A scale of 0 to 100. So it's numeric, right? 0 to 100. What is how it has been measured? Okay, so we're looking at performance of HSC students. To make it more interesting, let us say we are looking at the exam performance for the mathematics subject, okay, in maths. Makes it more interesting. For motivation, so study motivation, this was measured on a 1 to 7 scale. Okay. And study time, it was in hours per week. Okay, number of hours spent studying per week. So that's how the variables were measured. Okay, so again, we have those 3 variables. Okay, the dependent variable here, measured on a scale of 0 to 100. It's numeric, so we know we're all good. Here we have a Likert scale, 1 to 7. So you can imagine that it was a multiple item scale. So you have a whole for motivation measured using measured using multiple items. Very sorry about the dog box. I think my neighbors are outside in the yard, and that's the reason why I was working. Good. Okay, someone is joining in now. Nikshay Gumani, 6:20. Yeah. Okay, so here we have all our variables. I hope that's bearable for you, the dog box. So we have our 3 variables here, and let us now perform a regression analysis. Okay, so let's do that step by step. So first thing, let us run the regression. So to run a regression on SPSS, as you know, all your analyses are found here. You can analyze, and you find everything here. So guess where regression is found? Regression, right? And that's where you have all the different types of regression, which at least on SPSS you can perform. There are reverse, other type of regression which might not be included in SPSS. Like for example, binary logistic, multinomial logistic, ordinal regression, probit regression. So all those are different types of regression: nonlinear regression, weight estimation, two-stage least squares regression, etc. PLS, partial least squares. The one we're interested in is linear regression. Again, just that. And the same kind of logic will apply for the other. It's just the estimation techniques are different. So we're going for linear regression. That's what we need. We just click on linear. Okay, so analyze regression linear. Let me just reset that. I was just checking previously. That was working. Okay, what do we do next? Okay, I think you already can guess what the next steps are. It's very simple. Okay, I think you realize that SPSS is very user-friendly. You don't need to do any kind of coding, nothing of that sort. Everything can be obtained just with a few clicks of your mouse, right? So, but it's just that you need to know what you're doing. That's simple as that. So what's a dependent variable? What's the first thing you want to specify? The dependent variable like at performance, we just need to send it here. That's it. What about the independence, also referred to as the predictors, the explanatory variables? Study motivation is one, and the other one is study time. Those are here. And we're all set, all right? So we know that we want to estimate a regression model with academic performance as our dependent variable and motivation and study time, study motivation, study time as our independent variables, all right? And if we click on OK here, we'll get our results. Now, we have a number of assumptions that need to be met when we make use of regression. Without those assumptions being met, we cannot be fully confident that our results are going to be trustworthy. But our estimates are going to be really a good reflection of the truth, simplement. So we might be having estimation errors if the assumptions are not met. So we have a number of assumptions that need to be met. What I propose is that we look at the assumptions just afterwards, so that it doesn't really seem too much for you to assimilate at once. So let us look at the core results first, the main results, if we can call it so, and then we look at the assumptions. But en pratique, quand vous allez, when you're going to run the regression analysis, obviously you're going to run it first. I mean, at least at the same time. Okay, but for sake of explanation now, I'm just going to leave our assumptions. So normally what we will do, and we're going to do that next, to test with our assumptions, we need to choose a number of options. For example, we're going to go on statistics and then select collinearity diagnostics. We're going to select Dublin-Watson, and those are going to provide us with a number of results, values, which allow us to test for the assumptions. Let's forget about those for now. We just run the main regression. Good. So let us click on OK, and just like that, we're going to estimate our regression model. So we click on OK, and we have estimated our regression model, and we have here the results. So those are the main results of your regression analysis, and that's what you want to interpret here. So we got the model summary table, we've got the ANOVA table, and we have here the coefficients table. So let us see how to interpret those results, make sense of it. Let's be very clear about it. And then we look at the assumptions. Having done that, we'll be clear about linear regression. We would have completed that. But then once we have completed that, there is something else which we need to look at. We need to look at dummy variables. So specific cases, we have dummy variables, and also how to include control variables. That is what we do next, okay? So again, step by step. So we have the results here. Let us make sense of it. The first thing you want to interpret is this, whatever you have here, okay? Your R-square value from a model summary table. So let's take that and let's interpret that, okay, step by step. So that's the first table. Again, we're looking at the main results, right? Let me just send it on a Word document first, because when you send it on PowerPoint, for some reason, the formatting gets completely distorted. So, yeah. Copy that. Good. Just copy. And here we are, excellent. Okay, so let's quickly make sense of that. So that's the first thing you want to interpret here. Okay.
Sir, after the lecture, can you send us this PowerPoint?
Yeah, sure. Yeah.
Thanks.
Sorry, for some reason this is. Anyone knows how I can hide that automatically? Taskbar, hide taskbar, where is hide taskbar? Oh, um, yeah, okay. All right, so we have here our model summary table. What we want to interpret here is the R-square value. Now you see that you have a R-square and adjusted R-square. And normally, as a matter of good practice, just take the adjusted R-square. It's just an adjustment which is made to the R-square value, and you see here there's no big difference. When you have a difference of 0.003. So it just takes into account the number of predictors and then make an adjustment. You will see a kind of bigger difference between the R-square and adjusted R-square if you have many predictors, many independent variables. Why we do that? C'est que we models having a lot of predictors, the R-square value tend to get a little bit artificially inflated just because you have many predictors. So just because you're adding predictors, even though they do not contribute to the model, the R-square value tends to increase a little bit. Okay, so we want to account for that. So let's take the adjusted R-square, and that's what we want to interpret first. So of course we could have looked at the calculation as well, which is not that difficult, by the way, but we're going to focus on the application and the interpretation. Okay, otherwise we might get a little bit lost with the calculations and then yeah, you might not get the interpretation right, which is what we want to focus on. Okay. But I'll be sending you some further notes, okay, and you can have a look and in terms of how we calculate all the values, etc. Okay, so what is the adjusted R-square here? 0.703. That's what we want to interpret. What does that mean? The adjusted R-square 0.703. The first thing to know, okay, the R-square, which is actually referred to as a coefficient of determination. It is a proportion, okay? It's a proportion, so therefore it varies from 0 to 1, okay? It varies from 0 to 1. It cannot be less than 0. It cannot be more than 1. It's a proportion. So the value we get here is 0.703. What does that represent? It is a proportion of variance in the outcome variable. Okay, so let us say en termes général, the R-square, in the outcome variable, which is explained by the regression model. Okay, so the proportion of variance in the outcome variable, which is explained by the regression model. Now, it's very important to understand what we're doing here. And without really going into the calculations, we can still understand the logic behind. You see, we are interested in explaining academic performance, the outcome, in our example here, and not the same thing for whatever outcome we're trying to explain. We are interested in it because we have variation. We have variation. There is variance, there is variation. Some students have high marks, some have low marks, some have moderate level marks. Just imagine if for HSC, we're looking at the scenario here of HSC students in Mauritius, just imagine that we say, you know what, this year, because of COVID, every student are going to obtain 65 marks. We're going to just award everyone 65 marks. Then what happens then? I mean, on n'était pas trop loin la dernière fois parce que l'examen, not for HSC, but yeah, for Form 2, Form 1, etc. Automatic upgrade. We might as well have given such a certain mark. So let us say we give everyone 65 marks. Would there be any need for any kind of study trying to explain academic performance? Obviously not, because we know that any student would have obtained 65 marks. So it doesn't really, we won't even ask ourselves the question of how can we explain academic performance, variation in academic performance. Because to be specific, what we're doing, whenever we're doing research, we're doing quantitative research, and we say we want to explain the phenomenon. Actually, when we say we're going to explain it, what we want to explain, actually, we want to explain variation. Something happens or don't happens. Something is large or low or small. Something is high or low, depending on what you're looking at. And we want to explain that. We want to explain that. Why is it that some people are using, let's say, the metro in the region here, okay, region of Rosehill, Carbon, and started using the metro, and some are not using? What explains that? What explains that some people are doing vaccination and some are not doing vaccination? What explains that? What explains that some students have high marks for HSE and some very low marks? What explains that? So when we say we're trying to explain something, to understand something, at the end of the day, we're trying to explain variation. And even if that something was fixed, we would not even be interested in that. There would have been no need to do research into that. So we do research at the end of the day, and that's something very, very important to understand and to be very clear about it. Because there's variation, there are changes, because whatever concept we're looking at, those are variables at the end of the day. Somebody said that earlier, isn't it? That's something very important. As soon as we have a concept, we want to know what are the variables, how we're going to measure them. And measurement is all about capturing what? It's about capturing variation when you think about it. We assign numbers according to a set of rules so as to capture variation. You want to capture variation. And you do a test, such as a regression analysis, to try and explain that variation. So you measure something because you know it varies, otherwise you don't measure it. Once you measure it, now you know is it vary, it's going to take different values, there's variation. Now there's a certain phenomenon that varies, what we want to explain, and therefore we have a certain logic behind which we say, there are certain events, certain other type of variables, kind of other phenomenon, if you want, other phenomena, which are going to help us explain that particular phenomenon of interest, that thing what we want to explain, whatever it is. Okay, so what would your regression analysis? We're actually trying to explain that variation, actually. Okay, we're trying to explain variation. So coming to our example here, that's the first thing you want to know. So we are testing a regression model. What's our regression model? This thing here, which we have. Okay, it's a combined effect of all the independent variables. That's our regression model, which you can actually represent in the form of an equation. All right. And so if we represent that in form of an equation, it's going to take that form. So if we just take the notations y and x, it's going to be y equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus the error term. Okay, it can be written as e or epsilon. Today I heard that for the COVID we have an epsilon variant. I mean, nothing to do with that. Just an aside. So just using the notation that we have here, academic performance, okay, but dependent variable is equal to beta naught, your constant, plus the regression coefficient for the first variable, which is study time, plus beta 2, study motivation, SM, plus an error term. Okay, we're going to go in more details regards to that. But basically, when saying regression model, that's what we mean here, or regression model here. Okay. So you have your regression model. Is it really predicting that? And we can represent it visually as well. Okay, of course, you have an explained variance. as well here. So this R-square value is therefore very important and something you want to report first because it's telling you what's the proportion of variance. So obviously, the higher it is, you can guess, you would say therefore that your model is better. It's explaining more variance. The higher the R-square value, the more variance is being explained. If we had an R-square value of 0, it would have meant that our model was useless. It's not explaining any variance. We might do away with the model. The variables we have included in the model, in that case, study time, study motivation, do not allow us to explain any variance that we observe in ACAD performance. So it's useless. Heureusement, c'est pas 0. En fait, when you look at it, it's actually quite high, 0.7. Okay, it's closer to 1. We can simply convert it in percentage form, so 70.3%. And in fact, you will see in most reports, whether dissertations or papers, we'll have it in the form of percentage, just because it's more intuitive than proportion for some reason. So 70.3% of variance in academic performance is explained by the regression model. That's what it means. Okay, 70.3% of variance in academic performance, a outcome variable, is explained by the regression model. And that's the first thing you want to interpret. Okay, that's the first thing you want to report if you're writing your any kind of report. When it comes to the full interpretation, now that's the first kind of statement you will want to write, but then you need to proceed and elaborate on that. Okay, so 70.3% of variance is explained by the regression model. Is it good? Is it not good? Is it good enough? Is it what we expected, or did we expect more? If you compare that to the interpretation of a correlation coefficient, previously you've learned about the correlation analysis. Pearson correlation. As you know, for the Pearson correlation, we do have some guidelines, very specific guidelines. The guideline which I advise you to use is, of course, Cohen's guideline, where you say something like about around 0.2 is considered to be a small effect. Around 0.3, 0.4, medium effect, 0.5, 0.6, quite large to large effect. So you have specific guidelines. For the R-square, we might think about it relatively in the same way. So around 50% will be considered moderate, 0.5, so moderate to large. 0.2 will be small, quite small. And above 0.5, 0.6, 0.7, what we have here is on the large side. Just a broad guideline. It's not a rule, just a broad guideline. As a matter of fact, closer to 0, so the poorer model in terms of its explanatory power. In fact, we call that explanatory power of a model, by the way. When you look at the R-square, you're looking at the explanatory. That's a terminology which is sometimes used, explanatory power, ability, explanatory power, ability, relevance of a model. So if you have something which is very close to 0, it has low explanatory power. If it is close to 1 or 100%, high explanatory power en termes général. But when you're going to elaborate, and that's very, very, very important, especially for your dissertation, when you're going to work on that and you want to elaborate in depth, you need to make sure to discuss about it, taking into account previous literature, taking into account the context of your study, the context of the phenomenon that you're trying to predict. For some studies, why I was saying here that, because for some studies, something like 20% of variance explained can be considered to be already very, very good. For example, you're trying to predict happiness. Happiness is something, okay, which research have found is predicted to a large extent by your genes. So you have genetics, which explain already up to around 40% of variance in happiness. So some people are predisposed to be happier than others. And around 40%, imagine that, 40% of variance are claimed to be, is claimed to be explained by genes only. So this means that only 60% of variance is explained by external factors, by environmental factors. So if you're doing a study and you're trying to predict happiness of people, yeah, and if you get 20%, I mean, you can argue that your regression model is doing a pretty good job, because out of the 60%, you're explaining 20%, which is quite a lot already. 40%, previous studies have shown, are accounted for by genes, genetic reasons. You see? So in that context, in studies where you're trying, your outcome variable is happiness, well, 20% can be considered to be very good, a very good regression model, a strong regression model, a regression model with a strong, with high explanatory power, even with only 20%. You see, that's why when you elaborate on your discussion, on your interpretation here, you need to take into account previous literature. So in our example here, academic performance, when we look at the literature, you will easily find studies having obtained similar R-square values of 70%, 60%, maybe even some even went higher, 75%, 80% in some cases. Some models have been able to explain that. So when 70% is expected, okay, so it's good, it's very good, but it's in the norm. And if we had obtained something like 40%, it might not have been considered to be very good compared to other studies. And we might ask ourselves questions. Have we included the right variables, or did we miss some very, very important variables in our model? Okay, because we would have expected to have. As you might have guessed here, what's something which is very important. So if it is an outcome variable, if it is a phenomenon which has been studied a lot, where you have a lot of models already tested, so we know a lot about the predictors, you explain to improve on it. You expect to improve on it. Having said that, it might be, you test a model previously, a similar model explain around 60%, 70% variance, and you find your model explaining only 30% variance. What does it mean? Does it mean that your research is bad and it's crap? No, it might actually be very interesting, because it means that in your context, the theories maybe that you have used that are applicable in some other contexts are not applicable here in your context, and therefore that can lead to some very, very interesting arguments in terms of how the theory, the model that you have tested should be actually amended for future research. Might still be very interesting. Okay. But the point is that when you interpret the R-square value, it's something which you don't just take at face value. Okay, and this is where maybe we'll say also for master's level student, when it comes to a specific technique of regression, of course, but same kind of principles applies for all the different analysis. La différence se fait surtout par rapport à the level of analysis that you do after that, the follow-up. Okay, you just don't say that and you stop here. You don't say, yeah, you have a good model and you're happy. Okay, but in the grad level, it's good already. Okay, you got a good job and you don't expect a kind of super detailed explanation. But for master's level, that's where you need to do it. Good. Clara, I think your mic. Just mute. Sorry. Good man. Okay, so that's for R-square. What's the next thing? What do we do next in our regression? So let's go back to our SPSS. Okay, so we've just taken care of that. The next step is to look at the ANOVA table, obviously. Okay, the ANOVA table, we're still dealing with main results. So we take the ANOVA table. Let's copy that. And let me just copy that on the PowerPoint. And let's take care of that. Okay. So just so that we're clear about it. So here we're looking at, let us say, I'm just thinking about, and I'm going to send that to you. So maybe I just should make sure that this is clear for you when you're going to read it. So just make some small notes for you here. So one, we look at the explanatory.
Sir,
Right.
uh, explain our square value. C'est juste la phrase qui nous a écrit, 70.3 of variance in the academic performance is explained by the regression model.
Yeah, so that's the main one, the main sentence, if you want, you're going to write, which is like, yeah. And then, as I was saying, you will, of course, need to elaborate further after that, depending on the study you're doing.
Okay.
Yeah. So what I mean by elaborating is discussing the result in light of the literature, and this will depend on what research you're doing. So that is what I was explaining. Like, for example, so if we're doing the study on happiness, for example, 20% would have been good already. All right. So, for example, ici là, if you're doing a literature review, you would have come across a number of studies already, which have also predicted academic performance. Maybe in different contexts, not with regards to HSC students, could be any kind of context, right? So you're then going to compare your result, what you obtain, with that of previous studies, and based on that, you're going to kind of state whether your model is it explaining as much variance as you would have expected, okay, or not. So yeah, so that's the kind of things you can discuss on. You can actually at least say at face value it's good. At face value, that's a lot. 70.3% of variance explained. That's satisfactory. That's quite high. That's high actually. Okay, in terms of explanatory power. But again, how good it is, how good you consider it to be for your study, it depends on the context. Okay, so that's why I said always have this follow-up elaboration on that afterwards. Yeah. So just thinking about it, if you want to make, yeah, good. So yeah, who is it? Admin, yes, that's your name. It's okay. So at the same time, what you can see here is that you have so a large proportion of variance as well. So 29.7%, not large, but I mean, you do have 29.7% of variance, which is still unexplained and therefore accounted for by variables, predictors, which are not included in the model. Okay, so that's the unexplained variance. So you have 29.7% of variance, which is unexplained. That's something you can write as well if you want. So you say what's the amount of explained variance and what's the amount of unexplained variance. You can write that as well. And then again, in terms of saying how good it is, you really need to then look at the literature and look at the nature of the variable that you're trying to predict. Yeah. Good. So next we look at the ANOVA table, right? And now what we want to look at is the statistical significance okay, or we explain variance. In other words, your R square value. Right. Now, anyone can tell me why we need to do that? So what we're looking at here, we want to know yeah, anyone can tell me why we need to do that? So we look at here. You don't need to bother about all those values here. Those actually are values which allow us to calculate the F statistic and the significance value, but we don't need to do that manually. The SPSS has already given the final results, and we just need to interpret that. So what we're looking at here, we're looking at the statistical significance of the R squared itself. Why do we need to do that? Who can tell me?
Strengths of the regression model.
Yeah, yes or no, yes and no, because actually you're already kind of looking at the strength here when looking at the explanatory power of a model. So I won't really be using the word strength. Exactement, oui, mais then you will be kind of replicating what we said here, okay, in a way. So you can say it like that. More specifically, why do we look at the statistical significance of explained variance?
And the degree of relationship between variables.
Degree of relationship. Well, then again, I'm going to tell you that's what we're getting here, right? We know what's the, okay, it's high, so we know that you have strong relationships. No.
Statistical significance.
Yeah, that's the question. So why are we testing for statistical significance? What's the question? What do we mean by, actually, la question à la base, là, c'est what do we mean by, whether it's in the context of regression or not, or square or not, what do we mean by statistical significance? That's à la base la question que je suis en train de poser là. And what you should be able to reply with a high level of confidence, a very high level of confidence, better than 95%. Yeah.
Statistical significance has to do with the probability of the outcome was not by chance.
Yep. Yeah, exactly. Who is saying that?
It's Rajiv, sir.
Okay. You're appearing as admin. Okay, good, Rajiv. Good. That's it. So that's a probability. We're speaking of probability here. And why actually, if you can just tell me, why is there probability that the result might not be correct? Why? Why is there?
There are many reasons. First of all, perhaps the model itself was not good, or the variables chosen are not relevant, or the participants were not well chosen.
Yep. The main one, right? Of course.
Hello, sir. Can I just interrupt?
Yes, Abe. Yeah.
Is it a test for reliability? I
Sorry?
just heard Rajiv saying to test the yeah. I just thought it was a bit like test how reliable the research is. Is it the same thing? Or I'm just making confusions here?
Yep, you're making confusion. Yep. You're making confusion.
Okay.
So when we speak about reliability, we're looking at reliability of measurements. Well, You can speak about reliability of research overall, that's something else on very broad terms. But when we use the word reliability, at least when it comes to statistical analysis, so it's reliability of the measures. And we have measures, and we want to make sure that those measures are reliable. They're consistent over time, and therefore we can trust those. So yeah, so the word reliability would be used here in that context. Par contre, ici, yes, Rajiv, you're right. Okay. Now, misspecification of a model in terms of variables that are being added, that's one thing. Okay. But the most important one is the second reason you mentioned when it comes to statistical significance and why we want to test that. So whenever we do research, we are relying on a sample of observations. Okay. A sample observation only. And across fields, whatever the field of research we're doing, whether we're doing research in management, we're doing research in medical science, we need to rely on a sample of observations. Okay, and that's what we have. So if our regression model, which we're testing here, we're testing is based on like data from all HSC students, and we're interested in only those, then we might not even have to test for the statistical significance as such. Right, but if we look at the data set we have, here, we see that we have data for only 106 observations, 106 HSC students in our context. So whatever results, whatever coefficient, whether it's a coefficient of determination, the regression coefficient that we estimate, so whatever estimate at the end of the day is going to be prone to what we refer to as sampling error. There is a possibility that it is wrong. There's a possibility that it is wrong simply because we made use of a sample of observations. So it might not reflect the reality. It might not. So because of that, we want to perform an inferential statistical test and look at the probability of observing such an effect if that particular effect was not true. That's basically the reasoning behind. I hope that's making sense, okay, and that it's clear in your mind, type 1, type 2 error, whatever we did previously, that is stay clear in your mind. So in this context here, simply speaking, so we have observed, based on our observations, 106 HSC students, we find that among those students, at least, 70.3% of variance in their academic performance, 106 students, 70.3% of variance in academic performance over 106 HSC students is explained by the regression model. That's what we find. Are we interested only in 106 HSC students? No, we are interested in HSC students en général. Could be only for 2021, but could be as well en général. Depends on the research we're doing. But definitely not for only 106 students. So basically, we want to ask ourselves here, is it something which we might just obtain due to sampling error? Or is it something which is likely to be true? Okay, not something which we are getting just due to sampling error. Most specifically here, we're speaking of a type 1 error, and that's something we don't want to do. So there is a hypothesis being implicitly tested here. You don't really need necessarily to write it, but you can, why not? There is a hypothesis which is being tested. So whenever you see a f-test, whenever you see we're making use of a t-test, a f-test, a chi-square test, a z-test, we're making use of inferential statistics. We want to make inferences, right? And therefore, we're testing a kind of hypothesis, whether it's being explicitly stated or not. So here, this ANOVA result here, ANOVA table here, provides us with the result of the f-test where we're testing for the statistical significance of the R square. And what is your H naught? The H naught, c'est tout simplement ici R square is equal to 0, and your H1 R square is not equal to 0. And what it therefore means here, we're saying that the regression model does not explain variation in the outcome variable. In our case here, academic performance. And here, basically, c'est le contraire, the regression model, blah, 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 explains significant variation, okay, or sort of explains variation in the outcome variable. So that's implicitly the hypothesis that is being tested here. So we need therefore to interpret that. So here we're going to report the result. And when we report the result, we can include the degrees of freedom as well in our interpretation. So that's normally how we report it. So F, your F statistic, degrees of freedom for regression to report it this way. And is equal to 125.215. And then you got a p-value or significance value, p is equal to 0.000. Okay, so that's the core results here, what you need to report. What do we do? Okay, and this I think you already know. You know the rule, okay, and hopefully you understand the logic. So if your p-value, your probability value, your significance value here is less than 0.05, the significance level, what do we do? What do we do? Do we reject the null, H naught, or we fail to reject? Anyone? Yep. What do we do?
Reject the null.
Yep. So we reject H naught. Okay. We reject H naught. Just to help you to remember that, for those who really are struggling with that and really statistics is alien to you, just so that you don't get it wrong, we have a cute little phrase that statisticians like to use. So if P is low, if P is low, H naught has to go. Well, if this helps you, okay, if P is low, H naught has to go. Of course, low, you want it to be lower than 5%. Okay. Not just for those of you who are really kind of finding it hard, but I mean, don't just use that and then that's it. It's just to help you not do mistakes if you're still finding it hard, but then I trust you to make sure that you understand the logic behind type 1, type 2 error, and that it's clear why we're doing that. Okay, so we're rejecting our H naught, all right? So we're rejecting our H naught, and we therefore conclude that the regression model explains significant amount of variance in our outcome variable. Okay, what we're saying is that this 70.3% of variance, which we find here, 70.3% of variance explained in academic performance by the regression model, is something which is not really likely to be due to sampling error. Okay, so we can be very confident, at least greater than 95% confident that this result is likely to be true. Actually, we can't be sure about it. Okay, but what it really means, okay, c'est que if we're doing this study again and again and again and again, so we would be obtaining an R-square value very close to that 70.3% of variance. Actually, we can estimate the confidence interval and look at the lower an upper value as well. Okay, that's something which you can do in addition. But yeah, so that's the second main result that you want to interpret. Statistic and
sir?
Yep.
Sorry to interrupt. Can you please explain that sentence again? The F2103. Just the sentence, how you wrote it.
Yeah, so basically here we want to report what's known as a degrees of freedom. Okay, well, unfortunately, I won't be able to explain why it is 2 and 1 is 1 or 3, otherwise we need to go full into how to calculate the regression. All the calculation for the R square, etc., which is impossible in the time we have here. But just for you to know what we're reporting, c'est que we're taking here this degrees of freedom, right? So that's what we're reporting. You just need to report it. You don't need to interpret that. Maybe one thing which I can maybe just touch on quickly, c'est que let me take in the simplest case where you have only one predictor. The regression equation model actually at the end of the day is actually a straight line. So let us say we have y here, we have x here. So, and you have your different observations. So in the case you have only one predictor, the regression model is a straight line. And it's going to be estimated like that. And basically what we're doing, we're minimizing the errors, the sum of square errors. But still, your prediction won't be 100% accurate. So those are the real values, those are the predicted values. So therefore, we will always have, in most cases at least, a difference between the predicted value and the actual value. And this is known as the residual. And that's what we have here in terms of residual. Okay. So that's here sum of squares based on the regression, where you compare the regression model with actually, so what is comparing? So of course here it's comparing with something where you have sum of square errors. It's comparing with something else, which is simplement what is known as a baseline model. And the baseline model, c'est tout simplement your y bar, that is a mean value. So here for the regression here, the sum of squares that you have here, c'est tout simplement the deviations, the differences between the actual values and the baseline model. And that gives you here the sum of squares. If you take everything here, all the differences, you square them, you add them together, you get this value here, sum of squares. If you take
the same thing as mean deviation.
If it is the same thing, yes, for this one, if you're looking at mean deviation will be the difference between the observed value and the mean. Here we're looking at the difference between the predicted value based on the regression model and the mean value. C'est un peu différent. Yeah.
Okay.
Yeah. So, but that's the same idea actually. That's the same idea. Actually, what we call the mean value, the baseline model. Just imagine we were only looking at academic performance, right? So we have data about academic performance, and we want to predict the score of any student at random. So we have 106 students, and we just think about it this way. We're going to take one student at random, and let's say we're playing a game, and we want to be able to be as close as possible to the real value. So you know that academic performance is going to vary from 0 to 100. Someone might choose 0, someone else might choose 100, someone else might choose 50, etc. In fact, the best thing to do, the best guess you can make would be to actually calculate the average, because the average is actually the measure of central tendency, provided, of course, there are no major outliers and the data is not super skewed. That's an assumption. Provided you don't have very skewed data, roughly normally distributed data, the mean will be the best value, the value actually which represents the data the best. Okay, why is it the case? It's because it minimizes the sum of square errors, the mean deviations, if you want. The only reason, as you know, why we square it, c'est que for the deviations, for the errors, not cancel each other out. That's why we square it. Otherwise, you don't need to square it, but we need to, because if you have a central point, you have equal deviations above, equal deviations below. If you add everything together, it's going to be 0. So that's why we square it. So it's the same principle we have here. It's the same principle we have here. So if we're looking at the regression here, sum of squares, actually it's sum of square errors. Okay, what it is. So we're looking at the deviation for regression again between the predicted values and the mean value. So that's what we're looking at. If you look at mean deviation, actually you will be looking at the difference between the mean value and each observation. But here we're looking at predicted value and the mean value. And then for residual, we're looking at the predicted value and the actual values. Okay, so that's what we have here. So that's where you see we have a sum of squares for regression and residual here. And in fact, to calculate the F statistic, you just take. Sorry, just mute. Good. So that's it. Now, so for the F statistic here, because we're making use of those two figures here, so we just need to include, so what's the degrees of freedom which we have used to calculate each one of those. We just need to report it, don't need to interpret it. The 125, c'est quoi? C'est this value here, the F statistic. That's the F statistic. That's the F statistic. And at the end of the day, the only thing you need to actually interpret, say, your p-value at the end of the day. Okay. Yeah, so I think that's it. I mean, we can go into more details with regards to the regression estimation, but I don't want to do that because I really want to touch on all the important things when it comes to application. Is it okay? Fair enough? Yep.
Yes, good, thank you.
Okay, thanks. Good. So next step would be to look at the coefficients table. Okay. So let us just take that. Okay, so now we're going to look from the coefficients table. So first thing, we want to look at the statistical significance of individual effects. So that this has 3.1. And next 3.2, where we look at the relative strength . Another effect. And okay, the regression equation and prediction, if you want. Okay, So let's look into that now. Just say that. Qu'est-ce qu'il y a? C'était, do you want a small 5 minutes breathing time when we resume? Or not?
Yes, sir.
So can we start like 7:30? Is it possible?
Sorry?
Can we restart at 7:30? Is it possible?
Yeah, we take 10 minutes and.
Yeah, if everyone is okay. Huh?
Yep, okay, yeah, that's fine. Okay, so let's say.
We'll go till what time, Prince?
Sorry?
We'll go till what time? 8?
Yeah, so hopefully we can wrap up at 8. Yep, so that's the plan.
Okay.
We try to wrap it up. So let's say 7:30 we resume and then we wrap up at 8. C'est bon?
All right. Good. Yeah. Thanks. Sir.
Okay, good.
Sir, you will send the recording and the PowerPoints as well.
Yeah, I'm going to send that. Yeah,
Okay.
of course, sure. Mhm.